Hello viewers, welcome to IGCSE Computer Science Data Representation Crash Course 1. At the end of this tutorial, you shall understand how and why computers use binary to represent data. Understand the denary, binary, and hexadecimal number systems. Understand the choice of hexadecimal over binary in data representation. Convert between different number systems. Add two positive 8-bit binary integers and understand the concept of overflow. Understand and perform a logical binary shift on a positive 8-bit binary integer. And finally, use 2's complement to represent positive and negative 8-bit binary integers. In other words, signed 8-bit binary integers. Let's start with a big question. Why do computers use binary to represent data? Imagine that we have a phrase, computer science, which is supposed to be interpreted by the computer, and there exists in a computer a component that is responsible for processing data. Now, this component processes this data in binary form and stores the data in a register. Hence, we can extract from this illustration that computers use binary to represent data for two reasons. The first one is that computers only understand binary. And the second is that the processing component of the computer, which is just a logic gate, can only process binary data and store them in registers. To begin with, let's look at the first number system, which is denary number system. It is a base 10 number system which is made of 10 distinct digits, 0 to 9. Each number is written as a combination of one or more denary digits. The hierarchy of a single digit is determined by its place value, which increases by first powers of 10, starting from the 0 power, moving from right to left. For example, the place values of 215 could be written as 200, 110, and 5 units. Let's move on to binary number system. This number system is a base 2 number system, which means that it is made of two distinct digits. Because it's base 2, it's made of two distinct digits or symbols, 0 and 1. The binary numbers are written as a combination of 1 and 0. A binary number can also be written as a single digit, especially 1 or 0. These are binary numbers, and you can also refer to them as binary digits. Hierarchies of digits are determined by place values, which increase by the first power of 2, starting from the 0 power, moving from right to left. Recall that for base 10, the powers are for 10, and for base 2, the powers are for 2. For example, to represent the denary number 25 as binary, then we are going to have 2 in the place value of 2 raised to the power 4. Sorry, 1. The first one is in the place value of 2 raised to the power 4, which is 16. The second one is in the place value of 2 raised to the power 8. The 0 is in the place value of 2 raised to the power 4. Another 0, 2 raised to the power 1. And the least significant bit occupies the space for 2 raised to the power 0. For hexadecimal number system, it is a base 16 number system, which means that it is made up of 16 distinct digits. And those digits are 0 to 9 and then A to F. So they have to be distinct. You cannot continue with 10. So 10 means that you're combining 1 and 0. So the digits contained in 10 are not distinct. Hence, we are using extra symbols to represent the remaining digits in a hexadecimal number system. Now, these digits correspond, of course, to their denary equivalents, where A from 0 to 9 for hexadecimal are the same with 0 to 9 denary. Then A to F correspond to 10 to 15 in denary, as you can see on the table. Each hexadecimal number is written as a combination of one or more of the distinct digits, and each hexadecimal digit is represented as a nibble. So it means that each digit of hexadecimal is equivalent to 4 bits. So in a 2-digit hexadecimal number, 2D, we are going to have 8 bits to represent this hexadecimal number. Why must we choose hexadecimal over binary? First of all, it shortens binary data or saves space on the screen. Rather than writing 00101101 in binary, we could rewrite in hexadecimal to become 2D. It is easier for programmers to read, write, and understand. It is easier to locate and debug or correct errors. And again, what are the uses of hexadecimal? There are certain use cases where we could use hexadecimal in computer science. And these use cases include the following: MAC addressing system, color codes in HTML and CSS, error messages, location in memory, memory dump or debugging, IPv6 address, ASCII and Unicode character sets, assembly language, and URL. Let's convert denary to binary. In converting denary to binary, the following steps are recommended. The first step is to draw a binary denary conversion table and insert the denary equivalents of the binary place values. And the second step is, for any given denary, insert a 1 under the binary place value that is less than or equal to the denary, and 0 otherwise. We are going to illustrate this in a bit. And finally, you subtract the place value from the denary value to get the updated denary. So the formula is next denary is equal to previous denary minus place value. Let's take an example. We've been asked to convert the denary number 56 to an 8-bit binary number. And we start with our conversion table as recommended in the previous steps we enlisted. Now, the number is 56. With respect to the place values, we start with our comparisons. Is there any place value in the table that is less than or equal to 56? And that would be 32. So we place a 1 under 32 and subtract 32 from 56 to get 24. Now 24 is our updated denary. We start with 24 at this point. Is there any place value in the table that is less than or equal to 24? And that would be 16. We place a 1 under 16 and subtract 16 from 24 to get 8. We compare with 8 and we have 8. We fill the rest with zeros because we do not have any other thing other than 0. Hence, 56 denary is equivalent to the binary 001111000. Let's convert positive binary to positive denary. Again, we start with some steps to follow. Now, I don't want you to stress over the steps. What you can do is to pause the video if you think I'm being too fast and take note of the steps. Then during the example stage, you can pause the video again and try it out by yourself to see whether it works. And if you follow the steps, everything is going to work out for you. So let's start with the steps. The first step is to draw a binary denary conversion table and insert the denary equivalence of the binary place values. And the second step is to insert the binary digits into the table from the right hand side to the left hand side, starting with the least significant bit. And we add all the place values under which one is inserted. Hence, the result is the denary value for the given binary number. For example, when we are asked to convert the binary number 00101101 to a denary number, then we start again with our conversion table as usual and place the binary numbers under their respective place values. Now, what should we look out for? We should look out for the place values that have 1 under them. The first place value that we are going to identify is 32. And we add 32 to the next place value, which is 8. And the next is 4. And the last one is 1. So, adding these together will give us the value 45. At this segment, we shall convert denary to positive hexadecimal. Again, I will start with some steps. And the first step is to convert the denary number to a binary number. And we represent the converted binary in a 4-bit binary denary conversion table. Recall that a hexadecimal digit is equivalent to 4 bits. So 4 bits means enable. So having done this, we are going to insert the denary equivalence of the binary place values. We add all the place values under which one is inserted. Hence, the result is the denary value for the binary number from step 2. And finally, we extract the hexadecimal digits for the denary digits gotten from step 3. Let's look at an example. We have to convert the denary number 150 to hexadecimal. So we go ahead and do our conversion. Our normal conversion is nothing new to your other stage, so I have just gone ahead to perform the conversion without any strenuous set of steps. Now I will divide the tables into two and add the place values 1 to 8 for each of the groups, while at the same time allocating the binary digits for each place value. So these tables below look similar to the one above, except that we have two tables for the one below, whereby each table has the highest place value of 8. Now let's proceed, and we are going to extract the values. For the first table, we have 8 plus 1, 9. And for the second table, we have 4 plus 2, 6. Hence, 150 in denary is equivalent to 96. This is not 96, please. 96 in hexadecimal. Let's convert hexadecimal to binary and denary. Now, I always like to start with steps because they help you a lot when you are working on some task. So you can always use my steps here as a kind of reference. Should you solve any questions relating to number systems, these steps are going to be very resourceful for you. So the first step is to draw a binary denary conversion table to represent each hexadecimal digit and insert the denary equivalents of the binary place values. The second step is to join the binary denary conversion tables and reassign the denary equivalents of the binary digits. In a jiffy, we shall illustrate how this works using an example. And the last step is to add all the place values under which one is inserted, hence we get the result we're looking for. Now let's take an example. We have to convert the hexadecimal number CD to a denary number. Recall that each hexadecimal digit corresponds to 4 bits. So we start by getting the equivalents of each of these hexadecimal digits. The denary equivalent for C is 12 and the denary equivalent for D is 13. We get the tables for each one of them, and the corresponding binary for 12 and 13 have also been included in the table. For this, we combine the table. So instead of having 1248, 1248, we continue from the last 8. 1248, 16, 32, 64, and 128. And of course, the denary values remain the same. At this point, we add all the place values in our last table where 1 is placed under them. Hence, we get 205. In that case, the hexadecimal number CD is equal to 205 in denary. How do we convert binary to hexadecimal? The steps are simple. Divide the binary digits into groups of 4 bits from right to the left. So why do we need to move from right to the left? Imagine that you have a 7 bit to represent a number. So if you are starting from left to right to assign into an 8-bit register, then it means that you will get a wrong answer because your most significant bit becomes 8 instead of 7. So, but when we start from right, our most significant bit remains 7, except that we fill up the remaining space for the 80th bit with a 0. So the first step is to simply divide the digits into two groups of, or rather into groups of 4 bits, which are neighbors from right to left. And the second step is to draw a 4-bit binary digit conversion table and insert the grouped binary digits under their corresponding place values. The third step is for each nibble add the denary equivalence of the place values under which the binary digit 1 is inserted. And we write the hexadecimal equivalent for each of the denary numbers from step 3. Let's look at an example. We are going to convert 10101111 to hexadecimal. Following our recommended steps, we have each 4 group of bits represented using different tables. And we move on to work on each table. Now, if we are to convert this to denary, we are going to now combine the table and continue the assignment of place values at 16, 32, and so on. But because we want to end up with hexadecimal, we have to bear in mind that hexadecimal digits, each hexadecimal digit is equivalent to a 4-bit. So with that constraint in mind, we shall move on to get the values for each one of the tables. For the first table, when we add the values on the first table, we are going to get 15. And 15 is equivalent to F in hexadecimal. And for the one on the left hand side, we are going to get a 10. And 10 is equivalent to A. Hence, the binary number 10101111 is equal to the hexadecimal number AF. How do we get the maximum number length of a 4-bit, 8-bit, 16-bit, or what have you register? We have a formula that we can use to get this, and that is 2 raised to the power x minus 1, where x is equal to the number of bits. Look at the table below. For 16 bits register, that means a register that can hold 16 bits of data. Now, the maximum number or denary that can be stored in such a 16-bit can be gotten by the formula 2 raised to the power 16 minus 1, which is 65,535. It means that this register cannot hold any number beyond this value. In other words, when we have 65,536, such number cannot be stored in a 16-bit register. But the least register bits that can store such a number would be 17 bits. For 8 bits, the highest value that can go into 8-bit register is 255, and for 4 bits, the highest is 15. Performing binary addition requires strict adherence to some rules. The first rule is that 0 plus 0 is 0, and 0 plus 1 or 1 plus 0 is 1. 1 plus 1 is 1 0. This is not 10. This is 1 0 because we are dealing with binary. We have only 2 distinct digits. And 1 plus 1 plus 1 is equal to 1 1 and not 11. Note that if addition results in a 2-digit binary and a carry is required, the least significant bit must be included in the binary result, and then the most significant bit is carried over to the next higher place value. We shall be looking at this in our next example. Now let's take this example. Let's add 10101111 and 00011001. We start placing these values in a way that will be simpler for us to add them in pairs. Now to add these values, 1 plus 1 is 1 0, so we write 0 carry 1. We add 1 plus 1 again, which is 1 0, we write 0 carry 1. 1 plus 1 is 1 0, we write 0 carry 1. 1 plus 1 plus 1 is 1 1, we write 1 carry 1. 1 plus 1 is 1 0, we write 0 carry 1. 1 plus 1 again is 1 0, we write 0 carry 1. 1 plus 0 is 1, we write 1. And 1 plus 0 is 1, we write 1. So the addition of the binary numbers 10101111 and 00011001 is equal to 11001000. If this is a little bit difficult for you to understand, you can just play back the video and follow the steps, practice on your own along with me, and you shall be able to understand this better. Let's proceed. There is this error that is peculiar to computation of values in a binary register, and this kind of error is referred to as an overflow error. What is this error all about? It is a type of error that occurs when a number larger than a register can store is generated. For example, when you have 264 to be stored in an 8-bit register. This is going to cause an overflow error because the highest value that could be stored in an 8-bit register is 255. So having 264 will cause an overflow error. Let's take a practical example with an addition. To add these numbers together, we are going to get something scary. Our addition rules, following our addition rules, we add 1 plus 1, we get 1 0, 0 carry 1, and we have another 1 plus 1, 1 0, 0 carry 1. We have another 1 0, we write 0 carry 1, another 1 0, 0 carry 1, and 1 1, we write 1 carry 1, another 1 0, 0 carry 1, another 1 0, 0 carry 1, and yet another 1 0, we write 0 carry 1, and of course bringing this 1 to the values gotten in our addition will cause an overflow error. Alright, so I hope this makes sense to you, and you can feel free to play back the video, watch a number of times just to make sure that you're strong enough with the concept. Having said this, let's proceed to the next subtopic, which is on logical binary shifts. A logical binary shift can be said to occur when each value in a binary number is moved one place to the left or right. And there are two types. The first type is the left logical binary shift, which moves each value in a binary number one place to the left. It removes the most significant bit and creates an empty section at the right hand side of the register, which is then filled with a 0. Each logical shift to the left multiplies the binary number by 2. Take note of that. And the second type of logical binary shift is right logical binary shift, which moves each value in a binary number one place to the right. It then removes the least significant bit, which is the rightmost bit, and creates an empty section at the left hand side of the register, which is filled with a 0. Each logical binary shift to the right divides the binary number by 2. So the first one, moving to the left, multiplies by 2, moving to the right, divides by 2. Let's take an example. We are to perform a logical binary shift on the binary number, a logical left binary shift to be specific, on the binary number 01110001. So we are actually targeting that we are going to remove this particular 0 at the end of the exercise. And before we perform this process, we have everything intact. But at the end of the process, we are going to have that these values we now move one bit to the left, removing this particular 0. And of course, a space has been created because when they move one bit to the left, there is a space that should be created at the rightmost value. And the space is now filled up with a 0. So this is actually very easy to understand. Now the next is an exercise on a right logical binary shift. Let's move this particular value to the right. And before we move to the right, everything stays okay. And when we move to the right, recall that what is going to move in this case is this particular one will actually be removed. The 0 at the rightmost hand side, and a space should be created here. So when we move, we have that 0 moved to the right, removed entirely, and each bit moves one bit to the right, creating a space at the very end which is the most significant bit. And this space can then be filled with a 0. So logical shift is not difficult to perform. It's very easy. Sometimes you might be asked to convert the value gotten after logical shift to denary or hexadecimal, as the case may be. So you already know how to do this. You can go ahead and practice with the steps and watch the video so that you consolidate your knowledge on this. Now, logical binary shift shortfalls. There seems to be a kind of shortfall with regards to logical binary shift, and that is shifting a binary number whose most significant bit or least significant bit is 1 gives an unexpected result. Now, the default behavior for shifting to the left or to the right is that it causes a multiplication or a division by 2. But again, a left shift on the binary 10000100, which is 32 in denary, will result in 8, which is not what is expected. We expected that 132 be multiplied by 2. In that case, this reduces the original number rather than multiplying by 2. And on the other hand, a right shift on the binary, which corresponds to 45, will instead give us 22. How do we manipulate negative values in binary? We use a concept known as the 2's complement. It is a method for representing signed integers on computers. It uses the most significant bit to denote the sign of any given binary number. So it means that signed integers are integers that have signs, whether it's positive or negative. The binary number is negative when the most significant bit is 1, and negative when and positive when it is 0. So when the most significant bit is 1, the binary value is regarded as being negative, and of course when it is 0, it's regarded as being positive. The steps are simple. You convert the denary to binary regardless of the sign and invert the binary result. Then add 1 to the least significant bit of the inverted binary. The result is what you seek. Let's take an example. Let's convert minus 44 to binary. To convert this, we already know how to convert 44 to binary, and this is what we just did. Following our steps as recommended, the second step should be to invert. Inversion means that 0 becomes 1, 1 becomes 0. So we have 0, 0, 0, 0, which will be 1, 1, 1, 0, which becomes 0, 1, and so on. So having inverted this, the third step is to add 1 to the least significant bit, and we perform our calculation by adding. So when we add, we are going to get these values. Alright, so thanks for watching, and anticipate our next tutorial on data representation, crash course 1, crash course 2. You just completed data representation, IGCSE crash course 1, and coming up next is data representation, crash course 2. In case you've not subscribed to this channel, the only way you can help us reach out to so many other learners is by clicking on the subscribe button, and of course click the notification bell so that you will always be notified whenever we upload new videos. So this will help us to reach out to other learners like you and to support our mission of educating 10,000 people before the end of this year. Thank you for watching and see you in our next tutorial. Bye.